everybody. Thank you so much for coming. Thank you for joining me to talk about Elasticsearch, the most glamorous topic that you've got in this conference. I wanted to, before I get too far into the weeds, talk a little bit about sort of what I'm hoping that you all will take away from this talk, so that we have like clarity and expectations, and specifically to mention that if you come into this room and do not know what Elasticsearch is, this is exactly where you should be. This is the perfect room. If you already have some experience with Elasticsearch, that is also great. Some of the stuff that I'm going over will be, old hat for you, but I still think that there's useful things that you'll probably be able to take away to bring home with you to your practice as well. I want to specifically note that this is have a hands-on component if you want it. If you're not interested in trying to follow along as I go, this is all on GitHub. All of the materials are on GitHub, and you can go through this at your leisure when you get home and practice walking through this stuff and learn how these tools that I'm going to explain work. So absolutely no pressure. If you want to do it now, though, the GitHub link is there. It's also a shortened link at the bottom of every slide. So you can go there and clone the repo and be following along and build your own little Elasticsearch database and play with it as we go. Couple of notes. I'm not really going to talk about how to construct or sort of architect your own Elasticsearch database or cluster. That is an awesome topic, but not 30 minutes of material at this point. This is a talk where I really came into it thinking from the end user who needs to be able to access data in an Elasticsearch database that is normally working in R or Python in everyday analytics workflow. I think that there can be cases where enterprises will decide on a data storage system that meets the needs of a large-scale data sort of repository, but the end user is not necessarily the first concern when you're deciding which data store to go with. And so I want to help bridge the gap between the selection of the best data storage option for the speed and performance and the usability and the accessibility for someone who is just trying to write a report or do some analysis and get their day-to-day work done. So what are we actually talking about here? Elasticsearch is part of a family of data storage options that is casually known as NoSQL. Not the same as sort of tabular or relational database storage. I'll talk about things like relational databases, tabular databases as alternatives to the kind of thing we're talking about here. There are lots of differences, but we'll talk about the way that data is sort of conceptualized in the paradigm of data, and also the paradigms around how you communicate with a data store like Elasticsearch. These NoSQL databases, including Elasticsearch, are optimized for large-scale, relatively unstructured data, easy ingestion at massive scales, scaling up through infrastructure in a pretty easy way. And Elasticsearch in particular is worth noting is an open source tool, so it is free to use for the small scale user. As you scale up and need more resources and need more complexity, there are paid products, but for the average user who's building even a medium-sized data store, you don't need to pay anyone to have your own Elasticsearch database. And this is also useful to know if you go out after this talk and start Googling around and looking for information about how to implement this yourself. There are a lot of people going to try to sell you a lot of things, and you don't need to buy any of them, is my opinion. So then, there are some infrastructure and sort of architecture issues to know about Elasticsearch before we get into, okay, so how do I communicate with it? How do I get what I need out of an Elasticsearch database? And so I'm going to talk first about the data architecture. Now, this is not necessarily the same as the cluster architecture. When you're thinking about data in Elasticsearch, you should be thinking about indices rather than things like tables, for example, that you might come to from a relational database framework. An index is a user-defined grouping of data. It can be defined any way you want. You're the user. You get to decide what constitutes an index, what goes in it, and what doesn't. And we'll talk about nodes in a minute, but the architecture of the cluster involves a series of nodes. And your index can live on one node, or it can be split between two, as in nodes 3 and 4, as you see in the diagram. Or you can copy it. You can have a copy of the same data index on one node and on another. Have a backup and have an additional data object there that you can use for parallelized searching if you should want to. When you divide it up, it's called sharding. So you have one half or one element of the data index on one node and one on the other. They're shards. And so this is sort of the way to think about the data. It goes into indices, and that's sort of the big lump context for the data itself. On the other hand, the cluster architecture involves a cluster of nodes. So the master node, there can be more than one, but there's usually just one, is sort of the central manager of your whole data infrastructure. It manages where the indices go, which node the index is aligned to, which shard goes where, and moves things around in such a way that duplicates of the same index are never on the same node, because if one node were to go down for some sort of malfunction of some kind, then you lose both of the copies, and what was the point of having copies? And then it also sort of keeps track of whether nodes are operating efficiently, whether they're in good working order, and will alert you if one of your nodes has broken down for some reason. The master node doesn't know anything about the data itself. It just knows indices. Indices are the sort of unit that the master node thinks about. The data nodes, on the other hand, is actually where the data lives. That seems pretty obvious. But it also handles the infrastructure of sort of the actions that happen to the data, whether aggregation, whether it's search, that kind of thing is the data node's responsibility, and the node does it independently. So information requests come through the master node, they go out to the data nodes, and so if, for example, you have duplicates like we have on nodes 1 and 2 here, the searches will go on simultaneously, and so you have the advantage of speed of the searches that you might be doing. Also, if you have your data divided into shards, the data node 4 might not have the record that you're looking for because it might not be in the second half of index B. But data node 3 might have it, and it also might not have to go through as much stuff to get to the record that you need. So that's kind of the ethos around doing this in a clustered way, but also specifically the Elasticsearch form. And a lot of the stuff that I'm talking about right now is very general, and it's true of a lot of NoSQL data storage or distributed data storage methods. So I don't want you to think that Elasticsearch is the unique special snowflake in this regard. But this is a lot of the stuff that's very handy about using a data storage option like this one. So then, I want us to talk a little bit about search, because this is a concept that we have maybe a casual framework in our minds that querying and searching might just be the same sort of thing. That's not how I want you to think about it in what we're doing for this today. So for the specific context of dealing with Elasticsearch, search being in the name and all, is that searching is ambiguous, is foggy, it is uncertain, it allows you to sort of not know exactly what you need, and it will try to help you figure out what you need. And Elasticsearch is really targeted at this kind of a problem, where you have dozens and dozens of records, hundreds and thousands of records, whatever it might be, but you're not quite sure which record you're actually looking for. Elasticsearch wants to be like the helpful buddy who will go in and say, well, this one's kind of close to what you gave me, maybe this is what you want. And as we'll talk about later, it will rank the things it gives you back to help you decide which one is probably most likely what you needed. Querying or other forms of retrieval of data, which you could go into all kinds of different kinds, generally would be something much more specific. So the difference between Googling a term and maybe getting back something that's adjacent but actually what you needed versus having the URL exactly, knowing precisely what you want. You want no fuzziness, no ambiguity at all. Elasticsearch, designed for searching, but also designed for accessibility for end user experience to some degree. Because Lucene is the underlying technology that really is the data storage technology, but it's Java only. You can't get into it, you can't get anything out of it unless you're Java fluent. And I'm not, I don't know about you. So Elasticsearch is sort of on top of Lucene, allows you to get the data out in a more user-friendly way. And in this talk, we'll talk even about making it more user-friendly by getting your R or Python end user into it. So as I note here, Elasticsearch can handle all kinds of crazy things. Typos, it can handle fuzzy matching, wildcards, and conveniently, it can handle updating and matching simultaneously, which is not necessarily specific to the search issue, but it's just kind of a handy feature that I think is worth mentioning. So let's talk about the data itself and what you're actually getting when you're inside an index looking at data. And I have a tabular layout that comes out of, say, R at the top here, and the same data, roughly speaking, not quite the same amount, in the bottom half of the screen, showing you what a JSON sort of formatted nested data source would look like instead. So the tabular data, I think everyone feels very comfortable looking at tabular data, anybody from the person who uses Excel through the person who uses Pandas. But the nested list kind of thing can be a little bit sort of intimidating to look at first blush. But the thing to really keep in mind here is that you've got a chunk at the top of your record that is telling you what index you're on. In this case, and I'll talk about the data source in a minute, it's called Utexas. What type of information it is, it's data here, and so on and so forth. It has a record has a score because I searched to get this particular record, but the score is not important at this moment. And then everything below that in inner nest, the blue curly braces that you see, is the actual data that you would have in a row. And so then, once you get past the metadata that you wouldn't even actually be able to see in a tabular data set, you can see the information that we can pull out down here. And so let me tell you a little bit about this data source, because it's fascinating, and I believe they should get credit for having put together this data. The San Antonio Express News is a newspaper in Texas, and they have done a pretty exhaustive research on the earnings after graduation of graduates of the University of Texas education system, so the university system. And so what they've pulled are the aggregates at the major campus and graduation cohort level, and told us what their earnings are by the degree level, so bachelor's, master's, and so on, and also by the field of study. And it's a very interesting data set. It's not huge, but it's very useful. I have no affiliation with them or with Texas in any way, but it's fascinating data, and I just want to make sure that they get credit. And it's also in my slides in here and at the end of the deck if you're interested in learning more about them. So we're going to be looking at this data throughout today's talk, so you'll have plenty of opportunity to learn a little bit more about it. So just a little recap before getting into some of the more nuts and bolts of how we actually talk to an Elasticsearch database. Elasticsearch has a lot of advantages. Some of these advantages are general to NoSQL databases, but some of them are Elasticsearch specific. And one of the things that I want to mention that I didn't cover as much so far is the scalability. When you add additional nodes to your database, you have, there's a really pretty minimal resource intensiveness and like manual labor involved in adding more nodes for housing more data. So growing from a teeny tiny database like the one that I'm working with here to something very large is actually pretty easy. And doing a very, very small cluster is not a big deal. And so it makes the little database for your everyday use, it's not actually that crazy to try this out if you wanted to. Let's see here. So now I've already told you all about how search and querying are not the same thing, and now I'm going to tell you all about query language, and that's going to sound really silly. I promise it will make sense. For this purpose, Elastic query language doesn't actually relate specifically to querying. It's still about searching. I'm sorry, but this is the confusing jargon that we get to work with. So there's a way that you need to interact with Elasticsearch databases, not mandatory, but usually the best way to do it, that involves writing a specific query language using a specific syntax that Elasticsearch is optimized to work with. So you can, in some packages, and we'll talk about some of those examples here, use argument-based queries. So you can pass information to your Elasticsearch database through arguments and functions, either in R or in Python, and not have to write anything in JSON or curly braces. And that's possible for small cases. But I recommend trying the Elastic query language for a few reasons. It allows you full control of what your search says to the database. There are some real nuances. There's really interesting things you can do in the way that you communicate with your data, with your cluster, that argument-based querying may not allow you all of those options. Then there's another element that R and Python, the packages that we're going to talk about today, all accept query language. It can be the same query language, the exact same syntax that you pass to your R query or to your R function or to your Python function, and you don't have to change it at all. So if I'm working in R using Elasticsearch and I'm passing something to someone and using Python, for Elasticsearch we can just pass the same queries back and forth. Not a curly brace must be changed. It can be exactly the same. And I think that that's a really big advantage as well. So then there's some things involving aggregating and sorting that are really cool features of Elasticsearch that are just not possible through the argument-based querying at all. So I recommend giving it a try. There are disadvantages. Sometimes it can be navigably kind of complicated, but as also new versions of Elastic query language come out from time to time. So we're going to be using Elasticsearch 5.5. There are other things that I'm doing here. But when they switched to version 6, there are some things that got a little weird, or different at least. And so some of the things that I'm writing in the bash script that sets up the database that you could use if you're so inclined, some of those things have changed in 6.0. So, okay. This is the point at which, if you're interested in following along, this is available to you. Once again, I know they don't give you tables here, so writing code right now would probably be a little bit unwieldy. So if you're not interested in going through and following along, everything's on GitHub, fear not. But what you would do if you were so inclined is have Docker running, because everything that I'm giving you to work with here is involving using Elasticsearch in a Docker container. And then you just clone that repo and run a little bash file that I've given you that will set it up for you. And then the second step that you would run at your terminal, it loads the data that I've provided from the University of Texas to the database that you've just set up. So it actually all works real fast, and then you can start using R or Python as you prefer. So there are multiple libraries to use that will help you connect between your end user analytics sort of environment and an Elasticsearch cluster. And so none of them are perfect. One of them was written by some folks at my organization. It is not perfect, and I would not pretend that it is. However, it's pretty cool. It is the first one on this list, Uptasticsearch. The one big disadvantage of Uptasticsearch is that it does not support secure authentication. So if you are in any kind of organization that has highly secure data that you might be putting into an Elasticsearch cluster, it's not going to be the right fit for you, most likely. However, there are some other issues that are worth paying attention to. What kind of results do you want returned? If you're working on making this kind of data storage accessible to very inexperienced end users in the analytics space, returning JSON results can be really kind of gross. It can be a lot to work with, and converting it into a tabular data format can be very time-consuming and just clumsy. So Uptasticsearch actually does all that for you. It returns everything as a tabular data set already. So that can be really nice. It does not support argument-based querying. You have to write query language, which I will talk about a little bit more. But it is R and Python compatible, so you can use the same API in R or Python, and everything should work the same. Elastic is an R package that's just R, that does support authentication and does support argument-based querying, but it returns you JSON. And so, if you can live with that, then it might be the right fit. And elasticsearch-py is just the Python version that is actually supported by Elasticsearch organization. And so it's the formal official version of this. And there is support for argument-based querying, and it's just Python. So this is sort of the area that we're working in here. And you can just install either any of these as appropriate with pip or with install packages. So let's talk about the R options first, the interface in integrating with R. One thing before I get too deep into this is look at this little gray box at the bottom left. I've got notes and little tips and tricks all over this thing in little gray boxes. So this one is to just give you an idea of what the query string should look like. And we'll talk about different, more complex queries a little bit later. But where I have query string in yellow inside these code snippets, that's what you should go there. So if we're working in Uptasticsearch, the process is actually pretty simple. If you have spun up the database that's in the Docker container, these are all of the correct items that you should place in your query in order to get things out. And you can pass any query string you want in there as long as it's using the appropriate JSON in the Elasticsearch query language. Now, for using Elastic, the R package, it's also very similar, except you have to set up a connection to your database first before you can go in and start collecting data out of it. And then there is a formatting function that I've thrown in there that will pull the data out for you so that you don't have to view it in JSON format, but that's just not a super big deal one way or the other. You can do it if you want to, you can just handle the JSON. There are a few things that you notice in here about size and the sort of the amount of data that you would be returning. That can be important. There's also an element called pagination that's valuable to keep in mind both in the R and in the Python side. The non-Uptasticsearch packages will use a form called pagination, where you have to, after a certain number of records are returned, you have to use a function called scroll to get more records as it keeps going, because it doesn't want to accidentally you let you give it a query that's going to pull everything that is in the entire cluster and blow everything up. It doesn't want to let you do that, so it's going to impose a little bit of a limiter and sort of pace you, so to speak. Uptasticsearch says if you want it all right now, you can have it all right now, and if you're brave and you know what you're doing, then that should be fine. That's another thing to keep in mind with this query that I've given you right now. This returns every record in your database. If you are not working on the tiny database that is the example here, do not use this unless you are very sure how much data you're going to get. So finally, the last item on the bottom is the non-query language option, the argument-based option that is available through the Elastic package. And it's the same function, it's just now you're passing in the name of the index you want, the general it's sort of more of a regexy version of the query that you might give, and everything else is roughly the same. So here's our Python versions. Uptasticsearch, once again, you'll notice is very similar to the page that we just saw. Uptasticsearch looking basically the same arguments, which is the whole point. And then you'll need to, on the Py side, the Elasticsearch-py side, you need to set up your connection so that then you have that, and then you run the search, which in this case, because Python just likes to be interesting, requires a dict, not a string. And so here we have a string that goes to Uptasticsearch because it wants to be consistent across different languages. And then for the Python side, you need to use a dict. And then there's another option, actually requires another little package, Elasticsearch DSL, but it's really no fuss to get it. And that will allow you to run search using argument-based functions rather than using query language. I've also thrown you a little note over there, just how to get that query, the results of this query from JSON into a tabular format, if you're so inclined. I find that's helpful. So then, we have a general idea of how to talk to our Elasticsearch database, with kind of an idea of what it wants to hear, how to talk to it. So what do we want to say? There are options. The cluster is listening to you, and so now we're going to talk a little bit about how to write the queries, how to find out what you've got and get more information back. First thing to keep in mind here is that available fields is the first thing you kind of want to know when you start looking at a database you've never heard of before and don't know anything about. And it's not as easy as you might think to get that information. This is an area that I have nagged some of the people involved in developing these packages about. But for Uptasticsearch in R only, there is one way you can do that. There's an argument for that, or a function for that. And then if everything else, you can just use your database as it's spun up at the command line, just toss out a JSON document that will list the fields of the data set for you. It's not a big deal. It's just a little bit annoying to have to do. So let's talk about queries. Remember, we have our dict and we have our string. It really doesn't matter which one you need. The actual information that you're showing on screen will be basically the same. This is the same query, just spaced out and indented a little bit differently for everyone's convenience. So curly braces. This is going to be the problem for anyone who's trying to get really good at this query language. The curly braces are everywhere, and they're always, if you're me, there's always one missing. So if you have an IDE that allows you to do color matching of curly braces or of syntax in general, I would recommend it. It's great. It's really handy to have an IDE that will do this for you. But if not, it's OK. You'll figure it out. I promise it will get easier. So let's add a query like criterion. Let's add something to this that will now actually let us get some data that might be useful. So we're going to look for everybody who's major, all of the cohorts who's a major in computer science, and let's see what we get. Woo, we got some data. So now we only have computer science. That's great. That's what we asked for. Fabulous. But we also, let me see if I can get the laser pointer to work. We have little NANs over here, and we have little -1s in the cell count, which, as you might guess, cell count means how many students are in the cohort. This means there's not enough students to show the records without actually revealing, basically, the identity of the students. And this is private information. We don't want to show them your earnings data if there's just one of you in computer science at a particular college. So that's being redacted for obvious reasons here. So say we don't want to use that. We don't want to have a bunch of NANs and missing data thrown at all of our records. So we'll start doing this. We'll add a second criterion, which is right here, which is that cell count must be greater than 0. That's why they got the -1 in there. That's how they're identifying where something's been redacted. Perfect. We'll just go with it, and we'll add this. So now we have a couple of things that are different. We added the bool wrapper, which you can see right here, that tells Elasticsearch that multiple arguments are coming. It needs to be waiting for more stuff. And it also, inside the must, we added this straight brace on the side, square bracket, so that it knows that there's multiple query arguments coming in right inside there. And so that's really the major stuff that we needed to change. We just needed to add bool outside, straight braces, and then add range to the next section. And so now we get better data. We still got computer science, but look, no more NAs, no more missing. Everything looks great. Cell counts are all normal positive numbers. And so we're making a lot of progress, right? So there might be something else you want to do. What if you want to add computer science and then also choose which college campus you're going for? As you can see where we're going here, you could keep adding more stuff. So you keep those square braces, everything else can basically stay the same, and you just add another criterion to the middle, and we have new data. Now, I apologize that the column that says UT Rio Grande Valley is not present here because it got lost in these dots, but that's okay. Trust me, this is UT Rio Grande. And so everything else is the same, and we're just kind of pulling new records here. And that's the gist of how you would actually interact with your data set, or with your database. So just to revisit, you can keep adding criterion here till the cows come home. You have options of adding any sort of stuff in here and as you might have guessed, there are lots more querying options besides this. The search options in this infrastructure are pretty much endless because the whole point is that it's really good at searching. So you can do matching phrases, you can check whether fields are present or not present, you can ask where wildcards should be present and start giving it partial search terms and all kinds of things. You can exclude. There's a lot that you can do, and there's some links at the very end of my deck that will give you examples of how to do some more of that. One thing that I want to talk about briefly also is filter. Filter is a particularly interesting element because Elasticsearch is, once again, it's trying to be friendly, it's trying to be helpful, it's trying to get you where you need to go. And so the scoring element is one of the reasons that Elasticsearch is really good for this. When you add items into the query section, you're asking it to also score them. But if you want them to just be items that are used to restrict records, but not things that go into the score, then you use the section called filter. I'll show you an example. So here we have a query. This is similar to ones we've been looking at up till now, but now we've added a second section here outside of the first set of square brackets, and it has its own set of square brackets, and filter now gets institution ID. So we're putting institution in there, because maybe that's not a thing that we want to use to make our scoring. We're keeping major and degree level in the top. Now I'm going to show you the examples of the results if you do it like this, and the results if you move baccalaureate degree level into filter. Okay? So the first one, we have the degree level is in the query, and so it's being scored. And so you got 5.47 blah, 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 blah is the first score. And then if you move it, you put baccalaureate only in the filter. It's not part of the score, and you can see the scores change. So this is just to give you an example. Like, this is how the scoring can kind of work. And there are lots of things you can read about how the scores are really done, how the calculations work, and the under the hood stuff. It's very interesting, but there's a lot more to it. So in the interest of time, let me get quickly to the summarizing and sorting elements. So if you're using SQL regularly, or if you're using any kind of tabular, relational databases regularly, sorting your results is a very common thing. It's a thing you want to be able to do. Of course, Elasticsearch can do that for you. You just add, outside of the whole query, you add another section called sort, and that's inside your outer curly braces. So it's not complicated, but you now get the major title field sorted alphabetically. Everything else that we asked for in the query is also present. There you go. Summarizing, also a very important SQL functionality that Elasticsearch would not neglect, and it's a really cool thing that you can do with this, and I wish that I had time to show you more examples, but this is a really neat element that I can just give you a little taste of, and hopefully you can spend some time on investigating yourself. So here we're just going to take the title field, which is zip title for some reason, and then we're going to aggregate it into a new field called common majors. And as you can see, what is returned to us is a list of the majors and a list of the number of documents that are found in our database relating to each major. Very simple, and as you can see, it's a really simple query to write, and you can add into this other criteria, other filters, anything that you're already using querying before this point. Okay, So if you're following along at this point, one thing to do is you clean up the mess that you've been making. The data, this is basically a bash script that will close down the Docker container for you. You may not be familiar with doing that, but then you could recreate it anytime you like. This basically concludes what I have to tell you. There are lots of other resources. Once again, everything's on GitHub. The link is at the bottom of this slide. It's also at the top right. Please let me know if you have questions. I'm on Twitter all the time, and that is the best place to get a hold of me if you wanted to ask me questions about doing this or anything else that we do. And then once again, I want to thank the San Antonio Express News for putting the data together. So thank you very much.